In this talk, I'll tell you about two applications of transformers at Qualcomm, as well as some of the research we're conducting in quantizing these models. I'll talk about an application from my own team, the neural data compression team, where my colleague Jinhao Zhu developed a codec for images and video based on transformer-based components. And it turns out that when using these components instead of convolutions, you can design a much more efficient compression algorithm for images and video while retaining very strong compression performance. The second application I'll talk about is work by my colleague Davide Abati, who developed an attention mechanism for video super resolution. And the key idea behind this work is that one of the problems in video super resolution, namely the alignment of frames, that attention is very well suited for this, but it turns out you're wasting a lot of compute if you use global attention for this. And so what Davide did was design a local attention mechanism specifically designed for this type of problem. And of course, it turns out that you can improve the compute efficiency of this method by quite a bit. Lastly, I'll talk about a quantization scheme developed by my colleague Yelisei, which analyzes some of the problems in quantizing transformers, especially in the language setting, and introduces a couple of solutions. So how can we fix these problems, and how can we make sure that we retain a lot of the performance when we move from this high precision floating point model to a low precision fixed point model. And the main reason I think this is important, this type of research, which is focused on compute efficiency, is that a lot of the work we're seeing on transformers is aiming at scaling these models. Especially in the language setting, we've seen this huge increase in model size, billion parameter models. And the effect of that is twofold. First of all, we are going to use a lot of energy in running these models and in training them. And second, it is going to make it very difficult for others to reproduce what is going on in these labs that train these large models. So if we want to democratize the use of transformer-based models, we had better focus on making them more compute efficient as well. Again, one of the main reasons is we want to make sure that everyone can use these models, and that usually means that you can run them on various devices. And if only a couple of key players have access to these large models in hand, and they allow you to query them via cloud-based services, then that limits the ways in which you can use them. And additionally, from a privacy point of view, I don't always want to transmit all my text just in order to get a single prediction, or transmit my voice in order for my phone to understand what I'm saying. So I think also from that point of view, there's a very big incentive to try and make sure that we can run these models locally on as many different devices as possible, including very low power edge devices. I think one interesting work that I've seen in this area, although it's slightly different, it's not exactly aimed at the efficiency at deployment time, but more about memory efficiency. It's a survey paper by Google Brain, which I believe is called Efficient Transformers Survey from 2020. And the reason I think this type of work is important is that it gives you a very comprehensive overview of all the variations of transformers that we've seen appear over the years. So there are tons of variations on the name, X-former, Lin-former, and so on, each of which introduces a different type of attention mechanism or a different trick that allows you to compute this computationally inefficient attention in a much cheaper way. But it's very difficult to get an overview of this field. So how do all these methods compare and so on? And I think that's where the survey paper came in quite handy.